Hey folks, wanted to do a quick video here today, just kind of keeping us moving forward. I know we're getting pretty close to the end, but we do have some random topics that are continue to develop as we move through this modern physics unit, and we continue to review as well. Got two main topics I wanted to talk about. So as of now, we've talked about Einstein's photoelectric effect explanation, and then Millikan actually running the experiment and verifying that Planck's hypothesis was correct, that the energy of a photon is equal to Planck's constant times the frequency. In 1905, Einstein also devised his mass energy equivalence theory, and where he suggested that instead of having mass and instead of having energy, it was basically just mass energy, and they were two forms of the same thing. I know that's kind of a difficult concept to consider, but just bear with me. I'm not going to go through all the intense derivations. Um, but we can still utilize the equations for certain things. All right, so we've all seen the equation E equals mc squared. And to be quite honest, that was only a small part of Einstein's equation, which is shown below. But E equals mc squared. But in that equation, the mass is called the resting mass. So basically, this is the energy equivalence of any mass that is at rest. So if we could utilize all of the mass that an object possesses at rest and turn it into just raw energy, this would be the amount. Okay, and obviously, if we calculate this, we're going to get very, very large numbers because the equation is times the speed of light squared. But once we have something in motion, now it has more energy. So not only does it have resting energy, but it also has kinetic energy, or we can say it has momentum. Now, the reason I'm not going to go through all of these calculations or all the derivations on this, because it does get kind of tedious, but Einstein's actual equation is E squared equals PC squared plus MC squared, all of that squared, okay? But energy equals P times C. So we know the energy of a photon equals H times F, but energy is also equal to P times C, where the P is the momentum. And if we think back, momentum has an equation of mv. Now, this is where we run into problems because photons don't have any mass. Okay, but we can calculate this. Now, if we take that mvc and we multiply v times c, as v approaches c, we end up with mc squared again, okay? So it's just kind of another version of it. We can, once again, we can derive all of this out and we can get to our little 1/2 mv squared that we like to use, but the only way we can use the 1/2 mv squared is when we are traveling at speeds that are somewhat small. The closer we get to the speed of light, the more the energy actually deviates off of that equation. So once again, we're not going to get into all of that relativity stuff, but we'll just have to go with it. So since a photon has mass, or since the photon mass is zero, Einstein's equation just simply reduces down to E equals P times C for a photon, because the mc squared part of the equation is going to go away. Now, this is where it gets really, really challenging to think about. But yes, a photon does indeed have momentum. And we will see in, I think it's actually the next lecture, it has been proven that photons can impart momentum onto particles of mass. So photons do indeed have momentum. So if we rearrange E equals PC, we get, to solve for momentum, we have momentum is E over C, which E, once again, is H times F. So remember, wavelength is simply C divided by F. So this equation simplifies down to momentum is H over lambda. All right, so here's the deal. Unit for momentum, if we remember, is a kilogram meter per second or a Newton second. I still have a hard time writing the unit of a kilogram meter per second for a photon, because a photon is massless. So I tend to use the Newton second here, but use what you want. I did go ahead and solve for the practice problem that's shown right here and the one at the end after the x-ray spill. I'm just, instead of making a video on those and going through them step by step, they're pretty simple problems. So I'm just including a handout practice problem. So you guys will have access to the answer on that. All right, let's move to x-rays. So going back to Thomson, remember he used the cathode tube to fire the cathode rays, in which they thought they were another form of electromagnetic radiation, and he figured out that they were indeed electrons. Wilhelm Röntgen, I always want to say Rontgen, is Röntgen, ended up using the cathode tube as well, but what happened was he increased the potential at the cathode and it accelerated the electrons a little bit faster. And what happened was they started colliding with different films, and he ended up discovering the x-rays by accident, because what he found is that it traveled right through some materials, which we know that to be true for x-rays now. So to create an x-ray, what we need is a cathode tube, and basically we're going to use a very high electrical potential difference and then have it strike a target that is not going to go through. So we end up using the cathode rays, and we'll use a tungsten plate most of the time. Okay, the actual electric potential difference usually ranges from 30 to 150 kilovolts. Okay, so we're not talking about a couple of thousand volts here. We're talking about a couple 100,000 volts or up to it. Okay, so what happens is we heat up this filament and we accelerate these electrons. The electrons strike this tungsten plate and electromagnetic radiation is ejected. Now, this is almost, if you look at this, and we just finished up with photoelectric effect. And remember, with photoelectric effect, it actually went in the opposite direction. Photoelectric effect, we had the incident electromagnetic radiation, and that was used to eject the electrons, and now we're actually using the electrons to eject the electromagnetic radiation. Okay, so it's just a backwards form of this. So what happens is the electrons collide, and then it ejects the photons in the X-ray region of the spectrum. So pretty high energy waves. Now, for our calculations, we are going to simplify all of these. We're going to assume that all of the energy of these electrons, so remember these electrons are going to have kinetic energy, all the energy of these electrons come in, strike the metal, and then that is completely 100% transferred to the photon that's coming off of it. Okay, so there's no energy lost in this collision with the plate. This is the first actual film that was recorded by Röntgen. This is of his wife's hand, and you can see a ring on the hand. She actually made a comment after she saw it that she saw her death when she saw the actual film. What's kind of interesting, there's a lot of really cool history. Not to gross you guys out on these pictures, but, and I say cool history, it's actually not very good. And word got to America that Röntgen found these x-rays, and so then the rush was on to study them a little bit more. So Edison got a hold of this, and he had a lab assistant, and there's a lot of different theories and stories about his lab assistant, but his lab assistant supposedly volunteered, don't know how much pressure he was under on that, but to have photographs taken. So he was under the exposure of these x-rays for sometimes up to 90 minutes at a time. And what happened is these blisters started forming on his hand. The blisters ended up getting so bad that eventually he had to have some of his fingers amputated. And then these blisters ended up moving up his arms, and they ended up being cancerous, and the guy died from it later on. I think it was in a couple of years after these experiments were run. So anyway, these are just a couple of different pictures of the early x-rays. This is why they have to put the shields over us if we ever get x-rays done, because that's a pretty high energy ray. I mean, we get burnt just from standing out in the sunlight for a few hours and the ultraviolet radiation getting us, and now we're at a much higher region of the spectrum. Okay, once again, this practice problem will be on the handout that I'm going to post after this video. And that is pretty much all you guys have for the day. All right, have fun.